Just before we move on to looking at the shortcuts, I wanted to raise a awkward little issue in applying the nodal analysis algorithm just blindly, if you will, just following through the steps. And that is, what happens if you get a circuit that looks a bit like this? What is the current through that resistor? Well, we can see what the potential difference across the resistor is. We can see the value of the resistor, so we could apply Ohm's law to that and just work out the current through the resistor. And the simulator would tell us, of course it is. 1 volt across a 1K resistor gives you 1 milliamp. What might surprise you is to learn that if you put this circuit into just about any analog simulator in the world, it would fail to solve it and give you an error. Why? Because most analog simulators just apply nodal analysis. And something interesting happens when you apply the step-by-step instructions for nodal analysis to this circuit. Let's try it. We've got 2 nodes, neither of which is connected to ground. So we'll call them A and B. We have a voltage source here of 1 volt. And we have a resistor here of 1K. Now, since neither of these nodes is connected to ground, we apply Kirchhoff's current law to both of these nodes. We'll need to define our currents. Let's call the current up through this voltage source I1 and the current down through this resistor I2. Applying Kirchhoff's current law to node A would just tell us that the current in, I1, equals the current out, I2. And applying Kirchhoff's current law to this node B would tell us that the current going in, I2, is equal to the current going out, I1. We'll also have to apply the characteristic of a voltage source to tell us that VA minus VB is 1 volt, and Ohm's law to this resistor, which would tell us that VA minus VB is I2 times 1K. We have 4 unknowns: the voltage at VA, the voltage at VB, the current I1 and the current I2, and we've gone through the algorithm and found our 4 equations. Except we haven't found 4 equations. We've only found 3. The first 2 equations are identical. They're the same. We don't have 4 different equations. So we cannot solve for 4 variables. So a simple step-by-step, if you like, blind application of the rules would just result in a set of equations which has no solution. And this is what a lot of circuit simulators would actually do. The way round this problem is to notice that there is no voltage reference. You're trying to work out the potential at A, but relative to what? You don't know where 0 volts is. And 0 volts, ground, if it's not defined by a big stick being driven into the earth, is arbitrary. We can define our 0 of voltage to be anywhere we like. All the equations here will tell us is what the difference between VA and VB is. It won't tell us what VA is or VB is, it will just tell us what the difference between them is. And if we're trying to work out what VA actually is, we don't have that information. So, we just pick an arbitrary choice. And the usual arbitrary choice is to say that the negative terminal of the voltage source, or the battery in this case, is at ground. So we connect that to ground. And we define VB as being at 0 volts. And we don't apply Kirchhoff's current law to the ground node, so that equation wouldn't happen. We now have 4 equations in 4 unknowns, and we can solve them. If you're interested in how this simulator did get an answer, it's because this simulator makes that arbitrary choice for you. If no node in a circuit is defined as being the 0 volts point, this simulator will just pick one. Most simulators don't do that. I could find out which one it's picked by turning on show voltages, and it's made the sensible choice that the negative terminal of this battery is at 0 volts and the positive terminal is at 1 volt. But it's purely an arbitrary choice. It could have picked this node as being at 0 volts, then this node would have been at -1 volts. Everything would have worked out just the same. Okay, next time we really will start on the shortcuts, and the first of these shortcuts is a technique we've seen before, superposition.